So welcome everybody to today's talk within the Design++ speaker series provided to you by the Design++ initiative at the ETH Zurich. My name is Michael Kraus and I'm very happy to be your host today. It is my special pleasure to also welcome our guest and lecturer of today, Professor Karla Saldana, who is joining us from Florida today. Before I introduce you to our speaker and her talk, let me shortly provide some background information. Here you can see the overview of the lectures in this kind of series of the fall semester. And this is a recurring event, and we will provide invitations to upcoming talks in due time via email, our homepage, or our YouTube channel. Please find the updates on the dates, speakers, and topics in the homepage. You can also subscribe to our calendar to automatically import the invitations to this event. Please also feel warmly invited to have a look at our previous presentations. They are all hosted at our YouTube channel. You can see the link here on the right-hand side. At the moment, there is a number of professors from architecture, civil engineering, and computer science all across ETH Zurich involved in this Design++ initiative. For running the business, there is a team of 3 leading postdocs responsible for operating the Immersive Design Lab, together with some of the research and teaching activities. A growing number of scientists and chairs and professorships at ETH is associated to us. And if you're interested in the future of connecting AI, machine learning, and extended reality within the AEC industry, just reach out to us. We are very happy to inform and discuss with you about your ideas or projects. Having said all that on the background of Design++ and the speaker series, now let me introduce to you the speaker of today, Professor Karla Saldana, which is with the College of Design, Construction and Planning at the University of Florida. Karla is an Ecuadorian architect and researcher. In June 2021, so very recently, she finished her Ph.D. at ETH Zurich in the Department of Architecture with Professor Ludger Hovestatd. Her dissertation investigated the combination of artificial and human intelligence to have a precise and agile response to natural disasters. Since August of this year, Karla is a Tenure Track Assistant Professor in the School of Architecture at the University of Florida. Her teaching and research focus is applying AI in architectural practices at buildings and urban scale. So please also have a look at her papers and especially her homepage, which I linked here. And provided all that background information, you will also find on the YouTube homepage under the video associated to this talk. So that's basically all what I would like to say for an introduction. And now I would like to hand over to you, Karla. I think the stage is yours.
Right. So thank you for your kind introduction. So as you said, I'm recently assistant professor here at the University of Florida, and my focus is on the interplay or the relationship between artificial and human intelligence. The presentation we're gonna see today was my PhD dissertation, and is carried out at the intersection of architecture, disaster response, and artificial intelligence, and is entitled Event Protocols Enhancing Disaster Response with Architectonic Capabilities by Leveraging Machine and Human Intelligence Interplay. And throughout my talk, you will identify that I have used such an interplay between artificial and human intelligence in different experiments. And today's presentation, I organize it in 3 parts. So I'm going to present the research framework, a theoretical framework, and the last part is an application through experiments. And we start with the research framework. So this work pays particular attention to decision makers at the operational level, because they are the ones who know the current situation and are under requirements to be met in order to satisfy the needs of the affected community. And the decision makers are the ones that influence the short and long-term responses to natural disasters. The decision makers at the operational level are in charge of disaster response in 2 operations or 2 groups. And the first is called early response, which happened on the first days, and the second is called response, and this is the first weeks and months. And to carry such operations in the response phase, which is the focus of this work, decision makers at operational level should have access to valuable information regarding constructive and spatial constraints. In order to have an overview of such information, I conducted a systematic literature review on architectural interventions for disaster response that have a focus on technological approaches. And to tackle this literature review, I conducted a data-driven methodology to scan various papers with specific keywords and applied several filters to arrive at a collection of articles concerned with architectural practices in disaster response. So this is one of the experiments that I use in the interplay between artificial and human intelligence to navigate big data. So the total number of articles considered in this review was 4,300, and such number after the first filter got reduced to 701 articles. And those articles were fed into an unsupervised clustering algorithm called self-organizing maps, which is this grid that you're seeing on the screen. And this algorithm organized the data into major concepts. This sum grid allows us to continue with the following filter to reach a reduced number of specific literature that addresses architectural practices in disaster response with the focus of building and urban scale. At the building scale, the articles were subdivided into the following streams. So we have building safety assessments, materials for shelter design, and temporary, semi, and permanent housing after natural disaster. At the urban scale, the articles were subdivided into shelter location and urban design and planning. After the review, I found that most of the articles use data collection and visualization tools. For example, their articles focus on producing a mapping of the current state after natural disaster, either at the scale of the building or at the urban scale. Additionally, I found that several researchers used agent-based models and mathematical models to simulate and predict future scenarios. Both findings took advantage of data and computational power, which allowed me to help define the next question of this research, which is what are the new technologies to respond to natural disaster? So to answer this question, we will see many relevant attempts in the context of disaster response that used big data and artificial intelligence. But big data after natural disaster comes from many different modalities, which adds a layer of complexity when trying to work with it. From all the tools developed with big data, there is a solid vector for producing information for situational awareness that will later be transformed into a decision-making model with the help of artificial intelligence algorithms, which aim at finding a function that satisfies all the data points, predicting the answers when interpolating between points. These artificial intelligence algorithms have the characteristic of being created to solve problems. But now with the amount of data we have, they are not only solving problems, but they are dissolving them. Algorithms of artificial intelligence are classified in supervised and unsupervised learning. Both will be further analyzed depending on how they are used in the theoretical framework. What is important to stress is that researchers can directly use AI algorithms to create context-specific predictions or classifications without designing or training the algorithm's architecture from the beginning. Researchers can effectively encode image, textual, and spatial information characteristics on the data itself, allowing them to apply these algorithms to resolve architectural and urban planning problems in disaster response. So with this introduction, we found that technology is rarely used to bridge the gap between academia, government, humanitarian organizations, and civil society. We also observed an abundant production of data and scarce production of information. The difference between data and information is it's a key factor here, because data can be considered as this unorganized big data that we find online and on the web, and information, it's always pertaining to be this specific personalize, prioritize small amount of information. And finally, we noted a lack of information on constructive and spatial issues at the operational level for disaster response. So these highlights will be taken into account to formulate the gap that this research aims to address. So today we are exposed to a large amount of data and artificial intelligence algorithms. These algorithms analyze data in an agile and precise way. Due to their performance efficiency, researchers have started a trend proposing that such algorithms can replace several human activities. And this raises the question, instead of presenting AI as capable of replacing human intelligence, which approach presents it as a tool that augments the capabilities of humans to address various problems in specific disciplines? The amount of data represented in analysis makes it difficult to find relevant information for a specific situation. This prompts the question, how can decision makers at the operational level use AI to navigate the abundance of data represented in maps and extract relevant information to create specific models? 3 operations in disaster response deal with spatial and building properties, yet decision makers are from different fields of expertise, so they are not necessarily trained in architecture or urban design. So the former invites questioning, how can decision makers consider discipline-specific information when making decisions after a natural disaster? With that said, we started the theoretical framework, which is based on a personal reflection and a body of knowledge in architectural theory, mathematics, and philosophy that helped me identify a methodology that can address the research gap that I just presented. Now, this part proposes to use natural communication to relate maps and models through artificial and human intelligence and interprets them as tools and instruments. Our world is a complex and often inaccessible object of understanding. Therefore, it can only be described with abstractions. Throughout history, we have created apparatuses to abstract the world, such as maps and models. They reveal complexities in synthetic, simplistic, and partial way. They also facilitate ways of handling what we have but we cannot explain. The definition of the terms map and model is sometimes confusing, as both terms have been used interchangeably. Therefore, it's crucial to clarify the distinction between them to establish how these terms will be used throughout the work. So maps have been used to abstract and represent the world. In 1931, Alfred Korzybski introduced the notion that the map is not the territory. For Korzybski, the territory suggests a specific whole, and we will consider this the world, something beyond our reach. According to Korzybski, an ideal map will contain a map of the map of the map until infinity. For him, a map will never capture the world entirely because it is always an abstraction that freezes an interpretation. From those maps full of dimensions, observations, and data, models can be projected. These models are also abandoned, but the difference between models and maps is that a model is a personal projection. Models are treated in this work as a particular projection of maps. And such reflection fits with the assumption that models are specific, draw, projected, and are new things. So let us concentrate on the characteristics that differentiates maps and models between a purely numerical abstraction and a purely geometrical one. And the numerical abstraction, I call it a map, abstracts the world with any numerical representation to create categories and relationships. A map resembles the facts of the world with any dimension without projecting its data. The geometrical one, I call it a model, is an abstraction that deals with projections and perspectives. A model is projected by measuring the dimensions of the map to a reduced geometric space. A model is always a particular projection of the already partial map of reality. Both map and model are in a continuous relationship since one depends on the other. Moreover, they are in a quadruple relationship where to exist, a map needs a tool and a model needs an instrument, which then allows the communication between them. So to illustrate in more detail the difference between a map and a model, let us draw our attention to Geography by Ptolemy. The first book was dedicated to describe a tool, such as the stereographic projection, to create a map of the world. Furthermore, the following books are a list of coordinates that can be considered a map, to be treated with calculus and arithmetic. Ptolemy relies mainly on looking at the stars to create maps using multiple triangulation and multiplicity of guides. Such an approach is what this work considers a map. The second example comes from the 15th century Alberti's Treatise on Mathematical Foundations, the Scripto Urbis Romane. Alberti uses Ptolemy's tool as an instrument. An instrument takes distances on the ground to constitute connections and then uses geometry to articulate models. What Alberti presents us with is the use of technology of the time to create an instrument. Today's maps are diverse and are always changing as they are created with artificial intelligence and big data. Because one map is not enough to describe the world, we now face the challenge of producing models from these new and changing maps, hoping that such models will be the result of a personal articulation between the human's creativity and his or her exposure to a panorama of available information captured by a map. In 2017, the mathematician and physicist Elias Zafiris proposed a new modeling paradigm based on the mathematics of category theory. Zafiris emphasized that in nature, we do not have access to the things we would like to model because they are always encoded in geometric structures. So to decode the complexity of these geometric structures, he uses the natural communication to communicate the domain of geometry where nature encodes to the with geometric representations with the domain of arithmetic, where these geometric representations are transformed into numbers where relationships and categories can be found. For Zafiris, creativity consists on creating these bidirectional encoding and decoding bridges between these two domains that make a cyclical communication flow possible to embrace the current obstacle, which in this case is nature. And this whole construction is what he calls a metaphora. So returning to map and models, I suggest relating both concepts through the natural communication. Therefore, we consider a model placed in the domain of geometry, since it is a specific articulation of a map or collection of numbers, which then belongs to the domain of arithmetic. Therefore, to continually represent the world with a map and articulate a world with a model, I propose building an encoding bridge with artificial intelligence that will use a tool for mapping and the inverse decoding bridge by combining human and artificial intelligence to create an instrument for modeling. The main difference between a tool and an instrument lie in the interaction with the user's creativity. That is, a tool such as a lever or a motor, and an instrument such as a typewriter or a computer can be easily distinguished when observed from the size of how they are used. The instruments themselves have no particular use and are so generic that they require human interaction to articulate the result. In contrast, a tool itself is created for a particular and specific use and is defined for a certain action. Today's tools are supervised machine learning algorithms. These tools are used to automatically describe a reality in numbers that are then organized into a map. Current instruments are unsupervised machine learning algorithms, which are often used to create search engines that only articulate a result with human interaction. To better illustrate what a map is, let us turn our attention to today's most common use of map, Google Maps. If we follow our line of argument, we can understand that such a map is an organization of satellite images that represent the world in a way. It is a representation that, although useful, will never be able to completely capture the world. So to create this map, we use AI algorithms to process and analyze data. Let us suppose a machine that generates thousands of millions of static structures. For this example, a map on your lab will be an organized representation of all this data, or in this case, static structures. This organization is only possible by using artificial intelligence algorithms or tools that are capable of working with numerical representations of structures to generate an organized map. But the map is transformed into a model when a personal question is presented, such as wanting to know an address. On the left, we can see how a model is articulated, which includes a personal projection, allowing us to navigate through the city. Or on the right, we see a model articulated by asking a question to this hypothetical search engine, which articulates models tailored to such question. To continue with our subject, the object we are faced with is tailored to natural disasters. More specifically, we need to access the complexity of such entities through abstraction. And we found a similar aim in the metaphor of the map and models built around the abstraction of the world. We can therefore utilize such a metaphor and adapt the concept around with this new obstacle. Okay, I propose to use event protocols for the geometric model domain and map of events for the arithmetic domain, and the encoding and decoding bridges will remain constant. And thus the encoding bridge is built by a tool funded with AI, and the decoding bridge is an instrument that joins artificial and human intelligence. So in this metaphor, we have a general event protocol that contains all data referring to natural disaster in a geometric representation, such as images describing the occurrence of a natural disaster in different ways. Meanwhile, the map of events has where those geometric data were transformed into numbers with a tool of artificial intelligence, where we can recognize proportions, relationships, and categories. And with this organized map of events, an instrument is created by artificial intelligence algorithms and human intelligence to return to these personalized event protocols, where these geometric data that was previously abandoned and disordered are now organized to facilitate an informed response to a particular phenomenon. The human element is essential as it allows going beyond pure optimization routines by bringing creativity and reasons to the equation. And now we're entering to the third part of this talk, which are the experiments. So I have presented at the beginning this theoretical framework that deals with disaster response and decision makers at the operational level. And I told what are the things that are needed, which is this knowledge of spatial and constructive constraints in order to make decisions in disaster response. Then I have presented the theoretical framework that deals with how to navigate artificial intelligence within the framework of map and models, and how they can be used as tools and how can they be used as instruments in order to articulate personalized responses to any question. So here I'm going to present 3 experiments that I did on my PhD, which are creating this map of events and personalized event protocols using the metaphor that I articulate in the theoretical framework, which are trying to address operations in disaster response. So the first experiment I call joining narratives in disaster response, and is addressing the operation of building safety assessments. And the question I asked was how to cross-validate studies on disaster response with NGOs protocols to enhance involvement of specific disciplines in disaster response. Over the past 10 years, several disciplines have researched disaster response in 2 ways. First, researchers have published several studies using state-of-the-art technologies. And second, humanitarian organizations produce numerous protocols on how to respond to natural disasters. So to address the question that I just told you, This work proposes an experiment that considers both the knowledge produced in the form of 8,000 abstracts of academic publication on the field of disaster response and 2,000 humanitarian organization mission statements indexed online. And this experiment uses artificial intelligence in the form of a neural network to perform the task of word embedding and unsupervised machine learning algorithms for clustering. After clustering both narratives, we can now start a further filtering process to focus on relevant information. In the grid of humanitarian organizations, I took only the cells that share common terms with academic publications, and the filter for academic publications is based on finding common terms with a small group of academic literature with specific architectural focus. And we can also visualize those grids by showing their common narratives in a word cloud, and also transform them into numerical representations to be treated together by clustering to generate a common space, or what I call a map of events, where academic publications and mission statements of humanitarian organizations are sharing their interests. This map of events joins both discourses in an organized manner and serves as basis for prioritizing and selecting information depending on a specific interest. If a query is presented to the map of events, it can find a group of similar texts that are sharing the same concern. The outcome of a selection of this selection is a specific group of publications that we can consider tools and humanitarian organization mission statements that have similar approaches to the specific interest. So such an outcome is what I call a personalized protocol. And here we have two results depending on two different queries. So the output of this experiment are first, for future research, information on humanitarian organizations, on-site actions should be considered to provide a recommendation tailored to geographical location. So these are outlooks that I plan to do in my future research. And second, further research will work with lessons learned from humanitarian organizations because such data is relevant for decision makers at the operational level. The second experiment I want to talk with you is about how to use artificial intelligence for housing and shelter needs, and is addressing the operation of shelter and housing, reconstruction and construction. And the question I ask is, how can we create a decision-making model from multimodal natural disaster data that is tailored to the housing sector? One of the key challenges in disasters is combining the plethora of available data, ranging from social media data to satellite imagery, and turning it into concrete and actionable insights. This is especially true for humanitarian housing and shelter needs. Such operation deals with spatial and constructive constraints that, if not considered, can fail to achieve adequate solutions. Therefore, the objective of this experiment is to create an instrument that can guide the responses of decision makers at the operational level to address operations in the shelter and housing sector. For this experiment, I used three classes of data. First, disaster characteristics, second, location-based risk, and third, spatial conditions. And to ensure the scalability and low cost of this approach, I only used open and online data. For disaster characteristics, I used 202 disasters from MDAT database from 2010 and 2019. For location-based risk, I use the World Bank Global Urban Risk, European Commission Informed Risk, and UN data. And for climatic conditions, I use the sea temperature conditions at the time of the disaster. To capture the spatial conditions, I use satellite imagery from Google Maps. Because we often work in an environment that shares scarce data, or that data is not often available, we need to find online sources that allow us to really get the data that we need to work. That's why we chose to work with Google Maps. Since all the data collected by each disaster are from various sources, the modalities are equally diverse. Therefore, to deal with this multimodality, I apply a fusion approach at the decision level. So this technique allows to collect multimodal data to share a common semantic space that facilitates the prediction of individual variables. To explore the relationship of the 202 disasters, I used a machine learning unsupervised clustering algorithms, which visualize the events as a similarity of landscape, or what we call a map of events, where each natural disaster is positioned according to the similarity of its weight value concerning its neighbors. So what you're seeing here in this grid are the 202 natural disasters organized based on these 15 numerical features that we extract from each natural disaster, but are organized in a way that each natural disaster is close to similar or neighboring natural disasters. And in each cell, it will contain more than one natural disaster. So this map of events can further visualize each feature or describe a natural disaster to provide a detailed exploration. In this way, it is possible to identify which feature influenced the prediction the most. And the selected features that you're seeing here will be considered for future research. To create the personalizing protocols, I use data from 2020 on natural disasters. After feeding the new data to the map of events, each data point found a node which had the closest Euclidean distance to their numerical fused vectors. By comparing the prediction with the ground truth labels from 2020, each personalized event protocol achieved an 82% accuracy in the prediction. To add specific information to facilitate decisions in the shelter and housing sector, we will focus on the information provided by the Global Shelter Cluster, which has published recommendations for the construction of shelters and temporary houses. And these recommendations can be translated into a list of potential assessments that will strengthen the response and identify assessments that may reduce the effectiveness of the response. The final prediction includes the impact that the disaster will have on the community, and also show a list of recommendations on what to do and what not to do when making decisions in the shelter and temporary housing sector after a natural disaster. So this experiment allowed us to analyze a natural disaster as a part of a set of disasters that may show similarities according to the different characteristics considered. So in this present case, general attributes of the population and the sector were considered. While the attributes selected do not fully capture the complexity of the decisions in disasters, this approach provides a starting point to expand beyond the shelter and housing sector. The third project is called a Catalogue of Change after natural disaster, and it addresses the operation of urban policy. So the question I asked was how to correlate damage in the built environment with the corresponding investment to facilitate a decision-making model. After a natural disaster, especially in urban context, one of the first actions to be undertaken is a rapid damage assessment to assess the scope and scale of the damage caused by the disaster. One data modality that enables efficient and rapid damage assessment of the urban environment is satellite imagery. However, such survey won't provide reliable estimates of the cost of repairing or reconstruction, which could facilitate the initial fields and response. Hence, joining data about the disaster, the damage in the built environment with the investment needed for recovery will provide valuable information for various operations in disaster response. To address this question, this experiment uses the database created in the previous experiment. However, it selects a subsample of all the available features that was based on the conclusion of that experiment. Two new additional features, which have to do with the financial output from humanitarian organizations and the change in the built environment. So the first that as I told you, is data from OCHA's financial tracking service platform, where it not only includes the data, like the information about monetary information, but it also includes who was involved and when and what was the operations that they were carrying with that money. And the second is our satellite imageries from 2 specific dates before and after natural disaster. And this data needs a further processing to describe the damage in the built environment through a coefficient of change. So to create this coefficient of change, I first identified the buildings using an AI pixel-based semantic segmentation method with a 92 accuracy in segmentation. After the segmentation, the building layer was extracted as a black and white image of both stages, which permitted to calculate the difference between them, which then became the coefficient of change. So after extracting a coefficient of change in the built environment and the financial data to address such a change, it is time to perform a late multimodal fusion, resulting in a fuse vector for each natural disaster with 15 dimensions. These numerical vectors were fed as input to an unsupervised clustering algorithm to create a map of events. In this map of events, you're seeing these organized 50 natural disasters according to the similarities based on the several layers of information that describe each disaster. This map of events uses for visualization the geographical features of the most representative disasters in each node. But we can also use the images representing the change in the built environment of those cluster disasters and assign them to each node to visualize the consistency in clustering. With this map of events, we are able to articulate personalized event protocols that join 2 narratives: a coefficient of change in the built environment and the financial impact of that change. And actually, it additionally predicts the expected impact that such catastrophe will cause to the community. To validate this approach, we will take a natural disaster that occurred in Brazil in 2020, which you are seeing it on your screen now. And this selected catastrophe found a group of 8 catastrophes similar to it. By identifying the most representative case of this group of disaster, we can use it as a predictor of consequences, which means that responses to these disasters can be proposed as suggestions to the new case study. The final investment prediction, after this experiment, we identified that the final investment prediction was influenced by whether the country was in a conflict or not. So these actually set us as an outlook for future research. We'll dismiss such a data and only consider investment in natural disaster. And with these 3 experiments, we have demonstrated how one, by applying architectural concepts to the field of disaster response, can result in specific models that resolve some problems depending on the user's question. In this way, enhancing disaster response with architectonic capabilities by leveraging machine and human intelligence interplay. So after a natural disaster, the production of big data, instead of leading to an informed response, causes an overwhelming state that leads to data overload. To address this issue, several researchers have proposed methods for analyzing and visualizing this data with the help of AI algorithms. This analysis or visualization is what this work calls maps. They are necessary, but it is important to know that they are only representational. With the help of instruments built with artificial and human intelligence, we can articulate specific models to respond to a particularity of each event. These models are flexible and provide recommendations, but not only impose actions. By defining tools and instruments, this work provides an approach where human and artificial intelligence are augmenting each other's capabilities. The experiments presented in this work can be taken as a proof of concept. The next step will be to invite humanitarian organizations to utilize them. In future research, these experiments can be used together to form a digital platform where each experiment can be selected in accordance with the specific needs of the future user. This platform should have the capacity to grow to include more questions that arises from human experiences. Artificial intelligence algorithms improve the precision of their inference in proportion to the amount of data it is learning from. In disaster response, the problem is not So there is not enough data, but these data are difficult to access as they belong to several private organizations and are scattered across several online platforms. To access such data, one must acquire coding literacy. By being coding literate, one is equipped with the necessary knowledge to both access this data online and make decisions about how to process and fuse it through artificial intelligence algorithms to later articulate personalized event protocols to respond to a natural disaster. Thank you. So this is the end of my presentation.
Thank you, Karla, for this interesting talk and discussion. Your time and efforts are very much appreciated. As I said before, we will upload the information of this talk together with the video to our YouTube homepage. And eventually, I want to highlight our next talk about interfacing machine learning tools for creative users, delivered by Ardavan Bitgali, which will follow us from Carnegie Mellon University in the US in about 2 weeks on the 18th of November at 4 p.m. Zurich time. So thanks again for your attention. Stay safe and see you next time.